Hello everyone, I'm Ben from Heriot-Watt University and this is my flash presentation highlighting my PhD project, the study of elastomer blends for improved tyre performance, which is in collaboration with the German tyre company Continental. Tyres are vital to modern day global transport, and with over 15% of greenhouse gases coming from road vehicles, even small improvements in tyre efficiency would result in a considerable reduction in worldwide emissions. As you can see from this image of a dissected tyre, tyres consist of a lot more than just a hunk of rubber. In fact, their multi-component design has now led some experts to regard tyres as the most complex component on any vehicle, which I was quite surprised to find out during the start of my PhD. When designing a tyre with the materials we have available to us today, one must take into consideration the performance trade-offs described by the magic triangle of tyre performance, in which improvements in one direction often lead to detriments in the others. For example, improvements in fuel efficiency can lead to worse wet grip performance, which leads to poorer safety and handling, along with reduced abrasion resistance, which leads to more microplastic pollution and tyre waste. Therefore, this project aims to understand how the molecular properties of tyre rubbers impact the overall tyre performance, as an understanding of this relationship would help expand this triangle through refined composite formulations. There are many components in tyre rubber, but the main focus of this project has been studying the interaction between what are known as the elastomers and resins. The elastomers consist of relatively flexible, long chains of molecules and are the main components of tyre rubber, whereas the resins are short-chain polymers that are added as processing aids, but also have a large impact on tyre performance. Their use as processing aids allows for greater dispersion of the components within the rubber, which improves abrasion resistance. However, their impact on the mobility of the elastomer chains can vary. Generally, resins which are well mixed are said to increase the mobility of the elastomers, which can increase their elasticity and improve fuel efficiency of the tyres they comprise, whereas resins which do not mix very well can essentially clump up and reduce the mobility of the elastomer chains, which in turn can reduce fuel efficiency but improve wet grip capabilities. However, this relationship is not so cut and dry, which is why we are trying to gain a further understanding of the molecular level relationship with its real-life properties. So, how are we studying these rubbers? So far, we have done a lot of work using solid-state NMR, which relies on the magnetic properties of the molecules to gain insight into their behavior. We have also started work using radar, which is a novel approach that may prove useful for material testing in real-life environments. And we will also be using dielectric spectroscopy, which probes the electrical properties of materials and gives insights into their motions and structure, which we will be accessing in Hanover, Germany, through our collaborator Continental. Thank you for listening to my presentation, and I hope this has given some insights into the magical world of rubber.
Hello, my name is Toby. I am a chemist and currently doing my PhD in Wuppertal, home to the wonderful Schwebebahn and also one of the rainiest cities in Germany. And I have decided to do my research visit in the rainy city of Glasgow, Scotland, but more to that in the end. I am a polymer chemist, trying to synthesize various types of materials in my lab for electronic applications like lasers or quantum computers. The research focus of the working group I visited lies on conjugated polymers as sustainable photocatalysts for solar fuels production. What does all this mean, you might think? Let's take a closer look at one of the concepts in this rather infant research field, the hydrogen evolution reaction, HER for short. In a nutshell, the idea is to throw some polymers into water, let the sun shine on it, and that's how solar fuels like hydrogen are produced. No, not these plastics, more like this polymer panel. In reality, it's of course not as sketchy and simple. This research topic is quite new and has huge potential, so let's look a bit deeper into it. In this footage, you can see a thin film of active material coated onto glass. The irradiation with a light source causes the water molecules to split in a chemical reaction. Chemists have been familiar with the so-called electrolysis of water since 1789, the process of using electricity to decompose water into oxygen and hydrogen. Hydrogen is nowadays an essential part for energy, mobility, and the challenge to reduce climate change. But the stone-old electrolysis consumes more energy than the produced hydrogen provides, so scientists try to find more sustainable ways to generate solar fuels. Our approach are printable photocatalysts from conjugated polymers. These plastic electronics are chains of molecules capable of conducting electrical current that aids in the splitting of water. Similar to solar panels, the source of energy simply could be light from the sun. To improve the water splitting, it is convenient to add certain compounds and increase the electrochemical reaction. But this complicates the printing on a surface. Hence, we tried in this ScotChem project to chemically bond these additives to our polymer chains. Through that, we maintain the solubility of the materials in subsequent coating and increase therefore the efficiency of the hydrogen evolution reaction. The success of this novel concept led to innovative new projects to further investigate the water splitting with our materials. The ongoing collaboration between Wuppertal and Glasgow would not have been able without the support of ScotChem. I am grateful that I had the opportunity to broaden my academic scope, but also to visit the beautiful Scotland and create unforgettable memories. Thank you so much for your attention.